Good morning. I'm so excited to be able to talk to you about edge to cloud security today. So it looks like a lot of people survived last night. That's pretty good. And I'm so happy to see so many people make it to the last session of today. Can I first, before I start, get a raise of hands? How many people in the audience have actually used AWS IoT before? All right, good. And how many folks in the room are embedded engineers? Okay, good. So brace yourself. There's some C code in here, all right? It's going to be totally cool. My name is Richard Elberger. I'm a partner solutions architect in the IoT segment in Amazon Web Services. My day job is working with partners. For example, I'm specifically assigned to Qualcomm, Microchip, Texas Instruments, and Xilinx. And what I do is I work with them to help build solutions for our mutual customers. It's more like forward-thinking stuff, so we can prepare those materials before we actually engage customers. What you're going to see today are several scenarios that I worked with these partners on, all right? What you won't see today are demos. If you like some of these prototypes that you see today, I will be opening up those GitHub repositories after reInvent. So I'll have contact information at the end. You'll be able to follow me and then know when those content repositories become available. So let's go ahead and get started. Before we can really talk about security at the edge, we also just need to have a level set about what the shared responsibility model means at the edge, all right? You're probably all familiar about the shared responsibility model in the cloud. We'll define that for the edge and actually also define how some of those cloudy mechanisms help you provide additional security mechanisms down at the edge. Then what we're going to do is go through 3 use cases. They're going to be broken down by verticals. One is going to be an industrial IoT case. Another is going to be a connected building case. And the last one is for connected home. So they all have their different flavors, their different peculiarities. And then there's 3 types of security that we need to think about when we do security at the edge. One is physical, another is software, and then the last one is communications. So I'm going to matrix these topics across one another, all right? And you'll see that as we go through the slides. So first, let's go through about the shared responsibility model, just to level set on that and then look at what that means for the edge. You should all be pretty familiar with the shared responsibility model. The customer, you guys, you're responsible for the security in the cloud, right? So making sure that all your policies are in place, that you're locking down all your ports, all that kind of good stuff, right? And you're using the lowest blast radius that you can make possible to make your solutions work. AWS is responsible about security of the cloud. That means all the infrastructure and underlying mechanisms that help you build solutions. That doesn't mean we leave you to your own devices when you're doing responsibility in the cloud, okay? We provide a lot of services to you guys to help you build in that security in the cloud and audit that. And we also have a lot of partner solutions to help you out with that too. So you're not left alone in making sure that your part of the responsibility can be fulfilled. But that changes a bit when we go to the edge. When we go to the edge, this is software that is running on hardware that you own and operate if you're buying OEM hardware. Or if you're actually a device manufacturer, it's devices that your customers are eventually going to operate at the edge and probably work against some SaaS solution. So there's additional challenges that you need to overcome in compared to working in the cloud, right? And again, we have services that we've been providing to our customers to help you be more secure at the edge. For that, even though it's not really a shared responsibility model when you're operating at the edge. And we also have partner solutions, such as secure elements, to help you be secure at the edge as well. So for those in the room that are actually cloud first customers, you're very, very familiar. And a lot of the reason why you actually go to the AWS cloud is for those reasons that you see on the right. Everything is elastic, everything is available. You have high bandwidth everywhere. You have a totally secure environment when you have met your part of the shared responsibility model, right? But when you hit the left-hand side, there's a whole bunch of other challenges, including bad actors that could be operating in your own environments or your customers' environments that you need to overcome. There's one more part of this prism, though, that I want to express to you. We also have to, when we're doing IoT and building out these devices, we need to take care of the device lifecycle. And this is really broken down into 5 stages. The first part of that is, the first challenge really is, how do I get all these components for my contract manufacturer that's really related to supply chain? So all the components that you're putting on the PCB that's part of the product that you're creating and selling to your customers or you're putting in your own infrastructure are all of known origin. That's not something that we're going to be able to solve today, all right, for within this deck, but it's something that you need to be aware of when you're building these solutions. The next part, which we will be touching on today in the section about connected home, is what can we do to help mitigate threats around the birthing of the device. That's really, how do I turn the device on and then eventually connect to the cloud? With the cloud, with the AWS IoT core, you're connecting with the TLS 1.2 mutual authentication mechanism, right? So that means that you need to have a private key on the device that represents your device identity and an X509 client certificate that you're going to hand to the cloud to make that connection, all right? So we need to get those artifacts in place during the birthing process, and like I said, we're going to detail that in a later section. Where we're going to be working in most of this talk today is in the operating phase. And this is where the life cycle spends most of its time. And this is also where you need to curate the life cycle, how you're managing that device and improving the security of that device during that part of the life cycle. So that's why we have implementations in effect like over-the-air updates to help you improve the capabilities of those devices. The next part, which is something that we really can't help you with, is maybe you can do it in firmware or something like that, but it's actually the sunsetting of the devices. This is especially true in consumer devices. And I'll touch on that in the consumer section, but when you have consumer devices that you initialize in your home, eventually that's going to connect up to some system that has personal identifiable information on it. If you just take your device and throw it out the door, a bad actor could take that device and try to get the credentials off it so they can connect to that SaaS solution, right? So we have to take care or help our customers overcome these challenges when they're ready to dispose of their device. And then lastly, and when I work with silicon companies, they face this a lot, is where they have components that have been, let's say, repackaged, or they're being spoofed, or they're getting device packaging and they're reprinting the label with something else. And then bad actors are taking that and pushing that back into the supply chain. So you can see that that can be a maddening cycle. So you have to be prepared for the last part. And actually, these silicon companies that I work with, they have whole teams dedicated to try to ensure the integrity of the chips that they're selling to their customers, all right? So what do we do in the AWS cloud to help you overcome some of these things? Because you're not just left to protecting your device at the edge. There's a lot of challenges there, but we also have services up in the cloud that can help you overcome these challenges or detect those challenges. So your devices are going to be connecting to that service IoT core over a TLS 1.2 connection, and it's going to be using a protocol called MQTT to push data up into the cloud and receive data back from the cloud, all right? One of the aspects that you want to implement in order to detect that there's problems in your environment is Device Defender. And I just want to take an additional moment to talk about Device Defender here, because unfortunately I couldn't fit it into the slide deck for this talk to really detail this particular aspect. Device Defender gives you the ability to audit, to batch audit your devices against some possible attacks, or like, for example, duplicate certificates or revoked certificates, or some other strange behavior around those artifacts. But then we have the ability to detect behaviors in near real time. And when you do that, what you actually do is define a profile and you express the exact behavior that your device should be operating at. Like, it should be transmitting a certain amount of data throughout some threshold. And if the device is being attacked, there's likely going to be some variance in that threshold. And that's when we can actually take an alarm from that threshold and automatically do a mitigation action or send an alarm to SNS, so you'll get an SMS message on your phone. All right? And this is something that our customers are really looking at, because they're able to detect these problems early. And then feed that. After I get to past the left flow, I'll talk about the right one and how to feed the stuff from Device Defender into that. A way to also achieve additional security of your devices is to improve the intelligence over time. This is something that I talked about last year at reInvent in detail. This is a whole other topic about improving behaviors through machine learning. All right? In order to improve your behaviors for machine learning, you have to build up your data lakes, you have to retrain your models, and you have to somehow stage that in an appropriate way in S3, so you can eventually get it back down to the edge. Another way to improve the capability of your devices is to improve your firmware. So yes, people are using continuous integration in the cloud to rebuild firmware that gets applied to devices. Customers are doing that. But there's a couple of different ways that you feed in information into that development cycle. One is you're getting statistics from your device to figure out what kind of new functionality I can apply to my device to make my experience better. Another part of that is, how can I use analytics to see if my devices are behaving badly, or to alert me that I need to somehow update or overcome a security challenge? In the end, you're going to redevelop your not redevelop, but you're going to implement some additional functionality into your firmware to overcome that, rebuild it, and stage it. That's great, everything's staged, but how do you get that back down to your devices? If you're familiar with the IoT suite of services, the natural choice is to use device management for that and device jobs. We'll be talking about that in detail in the smart building section of the talk today, all right? But these cycles are there and exist, and you can implement these cycles today, all right? So let's move forward. What does it mean to have physical security, and what you have to take into consideration for physical security, all right? In industrial IoT. How many folks in the room actually work in industrial today? So, wow, more than I thought. So a real challenge with industrial IoT today, or has been historically, is that many of the protocols, and I'm talking about the upper side of the topology, the upper left side, many of these protocols, well, virtually all of them, have no security built in. All right? They're field bus protocols that are running mostly over serial, like a 485 connection or something like that. And you can bit bang these networks easy. So they're usually really, really locked down. But if you have personnel that has access to these control networks, then bad actors can do things to them. So you have to be prepared to mitigate those security risks. And also those risks happen at the software and communications level as well, right? But what we're seeing our customers do with Industry 4.0 is that they're taking data off these industrial networks and they're feeding them up to IoT Core so they can run analytics. And usually in larger control systems, you have multiple levels of firewalls and maybe secure tunnels and that sort of thing. But still, people are deriving the data from those networks and doing something interesting with it. In the lower part, you'll have video security networks. Again, those are not secured networks, but we're still aggregating that data and funneling that up into the cloud. And then in the middle, you have your normal IT networks that are generally well managed today. But in what's happening today, the paradigm is that all this data is being aggregated, many times using AWS IoT Greengrass, and then being pushed up into the AWS cloud. So we not only have to take care of the physical aspects of all these devices, but also the network aspects of these devices as well. Now again, between those aggregators that you see in the middle and AWS IoT Greengrass, unless you're doing something special with your aggregator, that's a TLS 1.2 connection. It's connecting to the MQTT broker in Greengrass using TLS 1.2. Likewise, from Greengrass to the AWS cloud, you're using TLS 1.2. So you have security in transit in those cases, but to the left-hand side, generally not. What type of physical attacks happen in industrial IoT architectures? Well, what we've been seeing a lot in the news lately are these side channel attacks. Generally, these only happen for super high value assets. But there's also another kind of attack that you'll see there called semi-invasive, and bad actors in those environments can put dongles within your systems to glean behaviors of your devices. Like if you're using certain voltage levels, or you have a lot of usage in your power network, in your control systems, that could actually signal, or they could resell that information to give some kind of competitive advantage about how much power you're using in your system, which could translate into how much products you're creating, right? So a lot of these things can come into play, and you have to really protect those systems. The case that we're going to look at specifically in protecting these physical networks is actually the tampering case. This will actually help or prevent a lot of these physical attacks that you see on, especially in the semi-invasive. If you can prevent tampering in your physical devices, then generally those first two columns will be taken care of, all right? But the problem is with tamper devices is that many folks have actually implemented electromechanical sensors to do that. Electromechanical sensors are prone to hacking events as well, because you can typically manipulate those using magnetics, right? So there's one way to actually overcome that type of hack, which is using inductive sensing. In this particular case, here where you see the microcontroller and the Wi-Fi module, I did this prototype using the CC3220SF, right? CC3220SF is qualified for Amazon FreeRTOS. I did the prototype with Amazon FreeRTOS. That microcontroller is also a dual-core Cortex-M4F. On one side, you implement your user application. On the other side is a network processor. So it's an all-in-one solution. You don't have a separate Wi-Fi module on this particular solution. Attached to this on this prototype was a inductive sensing sensor, which also comes from TI, all right? So when the door closes, you implement the coil so it gets very, very close to a metallic surface, and that could actually be the metallic door itself. When it gets close and senses that metal, then typically what happens is the pin pulls low. That way it uses very, very little battery power. What that translates to is that actually you can run that off of battery, right? Which is really cool. When the door opens and goes away from the metal, and it's super sensitive, so less than a millimeter going away, it will trigger a GPIO by pulling it high. So in Amazon FreeRTOS, and what we have is the ability to manage the priority of that sensing in order to effectively trigger these types of events. Amazon FreeRTOS is an RTOS, is based on FreeRTOS, which is an RTOS, which means it's a real-time operating system. It's a microkernel which is effectively a super smart scheduler. When you're implementing code using a super smart scheduler, what you're able to do is develop chunks of code. And the name for that, typically in RTOS, is called a task, and you can actually prioritize that at a particular level. So it'll run at a greater rate than other tasks that you implement in the code. So this is actually running at a higher priority That way I know that other tasks won't steal clock cycles from this task, so somehow it will skip some kind of sensing event. All right, so you have to take care of that as well. In order to do that, yes, I need to actually communicate that there's an event between this particular task, and if I want to send a message to an MQTT broker, I need to actually have a test that actually implements the publish to the MQTT broker. In order to communicate between two tasks, the paradigm is usually queuing. You can use a circular buffer if you want to, but usually it's queuing. In order to use queuing, you have to define a message. So I'm defining a message as a single character. Why am I not implementing this in JSON right here? The reason is that when you're working with microcontrollers, you want to keep the footprint very small, right? So you want to use the least amount of footprint as memory footprint as possible. So I'm just using a single character to flag that. In the task, it's a forever loop. It just runs forever. If the door is open, then remember, it's no longer sensing metal. It's going to pull the pin high. When it does that, oh, I need to fix that. When it does that, what it'll do is actuate some local GPIOs. Another case here is, though, because it is constantly sensing, it's not triggering an interrupt, right? So it is running in a loop. It's pulling. So I do need to check that if the state is the same. If the state is the same as the last time I checked, then I don't want to keep on sending the message to the queue, right? So this is how you quickly use this looping message mechanism, and then effectively at the end you send the message to the queue, and then the other task is ready to accept that message, right? Likely at a lower priority. When you implement that other task, though, it's also waiting for work to do. It's waiting for a message to come from the other task. So in order for this to not keep on running code all the time and stealing clock cycles, you can actually implement the listening of the queue in a blocking way, all right? Blocking simply means that it's waiting for some work to happen. So once a message comes in, then I can go ahead to that queue that I previously sent the message to. I can construct the JSON message. Why? Because I'm going to send it to an MQTT broker that's going to effectively consume that and likely propagate that to the cloud, where I'm going to use rules engine, right? So I'll put that in a JSON message, which includes the alarm, like where the alarm is it up or down? And also the ID of the box that I'm checking. And then I can finally publish that. Now, that's local actuation. I can send this to Greengrass, right? If Greengrass is not connected to the cloud and I'm relying on the cloud to send alerts that a physical tamper event has happened, then I might be in trouble. The cool thing about Greengrass is that it operates even when it's offline. And when it's offline, it'll actually queue those messages, so when it comes back online, it'll replay those messages up to the cloud, okay? So in local actuation at the Greengrass system level, what you're able to do then is check the status of the alarm, and the way that I implement it, I'm kind of skipping a step. So in the previous step, I'm sending everything to one topic, because I don't want to implement shadows on the smaller microcontroller to keep the memory footprint down, right? So I'm just sending to one topic all of the messages, but what's happening in that case is that I have a Lambda function in Greengrass that's working that and converting that into a shadow function, because that way I can use that in bigger box systems to do command and control. And then I can do local actuation. So what you see here is an event from a device shadow in Greengrass sending a message to a Lambda function, and I can do local GPIO because in Greengrass you have ability to interoperate with peripherals on the local system because it's hardware that you own and operate, all right? So if I'm disconnected from the cloud and I can't send a global message, then I can set an alarm locally, like a loud siren. That's something that's unexpected, like someone opened an electrical panel, happened in my control system. So let's go into smart building security issues and countermeasures and what the topology looks like in that case. The topology is actually a little bit similar to industrial IoT. The only difference is that you don't have a lot of those industrial protocols that are so diverse in nature, right? So industrial, you'll have like Ethercat and Profinet and Profibus and Modbus and all sorts of things, even bespoke protocols for control systems. But when you're talking about smart buildings, even for the top part for HVAC, on the bottom part for elevator systems, the common protocol is BACnet, all right? And then what we're seeing is that our customers are taking that data from these systems and propagating it up into the cloud so they can do analytics on that as well. But all of these become targets in these systems. Why? You may have heard a lot about ransomware and that sort of thing. So we have to take care of not only the physical, but also the software on these systems, because you can have all sorts of other attacks across physical, software, and communications. And then you'll have your aggregators in place, usually again, firewalled, because you want to have segmentation in these networks. And then you can send that to Greengrass and then through your border router. On the left-hand side, though, except for the middle part, on the top and the bottom, those are typically unprotected networks, BACnet networks. However, I can't, hopefully by the end of next year, I won't be able to say that anymore, because now starting this year, they are implementing BACnet SC, which is a secure communications form of BACnet, all right? So it's not gonna be implemented like immediately, but over the next 5 years, I hope to see that proliferated across buildings so it reduces the attack vector in those networks. Let's take a look at, though, the type of software attacks that we see in these types of networks. We are seeing people going in and doing permanent DDoS at the application level, also the physical level, but at the application level as well. Actually, what they're doing, what you may have heard in the news, is bad actors are doing ransomware, and they're saying, hey, I have control of your network, give me 50,000 Bitcoin, or else I'm going to do a permanent DDoS on your system. So we have to continuously take care of these networks and these types of attacks. So if we're talking about application DDoS, and for example, when these DDoSes happen, you have these bad actors out there listening to CVEs. And they'll read the CVE and then they'll say, let's go see if how many high value assets that are out there that I can go attack that haven't been patched, because they know what the issue is now, because that CVE has been posted. So that's a big problem. So let's see how we can overcome that in our own networks, because there's two parts of that, right? First of all, if there's a CVE for an OEM device that you're operating, then likely the manufacturer of that device will know of the CVE and fix the firmware and then deliver the firmware update to you guys. But the issue is that if you're managing, say, 40 buildings globally, you need to somehow get those fixes to control systems within these smart buildings globally. How can we achieve that? So two parts. One is we need to detect the issue. The second part is we need to deliver the fix for that issue, all right? So one part of that, though, on the left-hand side, the way that we prototype that, and I'll let you know the hardware that we use to prototype that, it's using the UltraScale Plus processor from Xilinx, which is a mixed criticality processor. Part of that is ARM processor that you run embedded Linux on. The other part of that is FPGA Fabric, where you can run stuff like the DNN-DK. It's a deep neural network development kit from Xilinx to do things like object classification and that sort of thing. One thing that we're really taking care of when we're implementing these building systems are separation of concerns, right? Or sandboxing between these systems, like what you saw in the first topology. But the case that we were thinking about is if we were going to implement a building management network for a small building, like smaller buildings, if it's a small medium business that's running a few buildings, how would they implement that while keeping the bill of materials low, right? how can I implement that kind of segmentation using that same processor to keep our customers safe? So what was implemented to overcome that was something called Siemens Jailhouse, where you can run what's called cells. Cells would actually be, they're kind of like VMs, but they operate at a lower level where they have a lot more capability to do hardware handling and memory sharing between those cells. So that means if I have memory sharing between these operational cells, I can actually, and I'm effectively talking about if one cell goes down, then the other cell can be like the watchdog or the maintainer of that other cell. So if you can overcome that problem, then you can actually trigger it to reboot or whatever. Actually, what you can also do with Siemens Jailhouse is have set up virtual networks between those cells as well. So now what the building management system can act as, it can act as a greengrass device for the greengrass system that's running on the other cell and has direct internet connectivity. So now you have separation of concerns even when it's on the same system. When we're running, though, in that closed system, using the building management system, that's also managing that backnet network that has all those devices on it, and one family of those devices could have a CVE, right? And we want to upgrade those the firmwares on those devices. In order to figure out if there's anything weird happening in those networks, we need to get data out of that network and into Greengrass and ultimately up into the cloud, or to understand the operational behaviors of that. So if the building management system is acting as a Greengrass device, all I need to do in Greengrass is set up a subscription, or synonymously called a route, in your Greengrass group that says, if data is being generated from the building management system, which is acting like a Greengrass device, and I want to send that data to the cloud, I can run that against a particular route, a particular topic, right? So you would actually, in the fullness of implementing your solution, you would have a lot of these routes because you'll have many of those control systems throughout your building. Likewise, if you want to do actuation within your backnet network, and your building management system can handle that, you can trigger that by also implementing those backnet systems as things up in the AWS cloud, simply so they can have shadows. If you implement them as things in the cloud, in the AWS IoT core, and configure them as part of your Greengrass group, then you can get shadow synchronization down to the Greengrass core. Now what you can do is actuation from a cloud perspective down into your backnet network, as long as your building management system is aware and able to do that, all right? So from that, what I can do is actually send another route from the shadow service within Greengrass, listening to a Delta topic in the case of if I want to perform actuation within my building management system, and listen to just that change and send that message accordingly to that Greengrass device up in the building management system that is functioning part of the building management system. And then likewise, what we want to do is send data back in. If you want to get data back to the edge, you can do that as well by setting up routes up from the cloud down to the edge, or you can actually set what you want to do also is actually do some local functioning within Greengrass. You can run that through a Lambda function and put that message back into the backnet network as well. But if I'm just sending data to the cloud and I want to monitor my systems for weirdness, usually you're at some steady state, right? And when you're looking at analytics, you want to understand if there's any variance in the process to identify if something's bad happening in your network. In this particular use case, what happened is that a CVE, the case that we want to communicate to customers, if something is known and an attacker is directly attacking your backnet network, and we can identify fluctuation in your process, we can have an upper threshold of normal operational state, a lower threshold, and then we can identify the outliers and what's causing that. Actually, AWS IoT Core has been doing this kind of anomaly detection for quite some time. This isn't something new that was just invented in the last year. This particular chart came from a blog that was posted about 3 years ago, but the same principle still applies. So once you know the outliers, they can, analysts can will actually look at this and say, hey, what could possibly be happening here? And if they figure out that it's actually some kind of attack coming from those, some kind of attack happening against those devices that could be a result of a CVE that they located, then they can go back to the OEM, grab the firmware, and then deploy that to those devices via the building management system. All right, today what's happening is people are downloading these new firmwares and manually putting in the building management system. We want to cut all that manual stuff out of the picture. So in order to achieve that, we can use device management. To use device management and take binaries that you've created, either your own firmware that you're developing or firmware that someone else developed and you want to proliferate through your networks. Usually what happens is you use Greengrass to facilitate the copy of that firmware down to the edge. You usually do that by leveraging a pre-signed S3 pre-signed URL. In order to get an S3 pre-signed URL and ensure the integrity of that binary after it's been downloaded from the cloud, you want to actually sign that binary, right? The way signing works in the cloud for this particular purpose is by using a service called AWS Signer. In AWS Signer, first what you need to do is create a version bucket to hold that image. That's a requirement. The next thing you do is define a source and a target. But this is, or a destination, and the meaning of the destination doesn't mean that the binary moves from one S3 bucket to another when you're performing the signing operation. Actually, what's happening is the binary stays in the same location because it's a versioned object. In the destination, you get a file that includes the pre-signed URL, and it also includes the file location and the file size and that sort of thing. You're going to take that file and actually make it part of the device management job, right? So when you start a device management job in AWS IoT, you actually create a job. You need to provide a job document, which is a JSON document. In that JSON document, you're putting that pre-signed blob in there with the pre-signed URL. Sorry, I totally messed that up. The blob of text from the signing operation, part of that blob is the pre-signed URL. When you create a job in AWS IoT that gets sent to a topic, when you create a route, just like the routes I talked about, in order to transfer the information that's going to that job topic up in the cloud down to the edge, now IoT Greengrass can perform operations on that job document on the actual target device's behalf. So when I'm creating a job, I'm not creating a job to change the firmware of the Greengrass device. I'm creating a job to change the firmware of the devices that are in the backnet network. I'm just using Greengrass as a proxy for that particular purpose, right? In that case also, I'm not going to define every single device that I'm going to apply this firmware to. What I'll want to do is use thing groups in order to define that. Thing groups is a capability in IoT Core to logically group your devices. It also enables you to do things like indexing and so forth. But in this particular case, you feed the thing group to the job, and it says, okay, I'm going to create a job, and that job is going to manage the status of the execution against all those particular devices. All right. And then you can monitor the status of that job. You're not actually monitoring the status of each individual device. When you set up a job, it's setting up one management, I would say, action for all the devices that belong to that particular thing group. When you start that job, actually the topics that it's sending the job document to, the topics themselves look very similar to shadow topics. So when those messages get sent down to the edge, and the building management system is performing the action, and it's like 75% complete, 80% complete, 100% complete, it's actually sending status messages back to Greengrass, from the billing management system back to Greengrass, and then from Greengrass up into the cloud. And then centrally, you can manage the total status of your job. All right? So from there, let's talk about communication attacks. I'm starting to lose my voice. It's been a long week. I apologize for that. For consumer IoT, though, the networking challenges are a lot different. The previous two topologies that I talked about, those topologies will be curated by IT departments. In smart home, your IT department is the end consumer. It can be anyone at any particular skill level, right? They may know about security, they may not know about security. As people that are creating devices for our customers, we need to help them be more secure. Also, in those topologies, you may or may not have Greengrass. In many cases, these devices are still directly connecting to a border router. I have a single border router in my house. I have a lot of other routers too, but a border router in my house. Things like Alexa need to have a direct TCP connection to the cloud. It can't be run through Greengrass, right? So you don't have that middleware that can help curate that security. So we need to think about that as well. So all of those systems in the ecosystem become targets. Who do they become targets from? It's your house, right? When you think about it, you have workers coming into your house all the time. People that are doing paint jobs, people that are fixing your HVAC unit, people that are implementing light switches in your house. They could be anyone. You're not doing a background check on them, right? So we still need to have the mechanisms in place to help protect our customers in these situations. In the top part, also in connected home, those aren't BACnet. What's happening usually is the thermostat is directly connected to the HVAC system, and the HVAC system normally has a Wi-Fi module that's directly connecting to your border router. So those are all challenging aspects, but we need to help our customers take care of that. So the type of attacks that we've seen in smart home for communications is mostly about device identity and stealing personal identifiable information, right? Once they get your identity information, then they can do things, everything ranging from blackmailing you to stealing money from you to racking up your credit card. If we're implementing those devices, we need to help protect our customers against that. So the case that I'm going to talk about in this section is related to device identity theft. Now, when you're using Amazon free RTOS, you're like, if you're in a prototyping stage and you're tinkering, you're going to start using something that's called dev mode provisioning. Dev mode provisioning is because when we connect to the AWS cloud, well, IoT Core, you're doing TLS 1.2, mutual authentication. You need a private key and a certificate in order to achieve that, right? And somehow that certificate needs to get onto the device. When I'm prototyping with Amazon FreeRTOS, I'm putting the private key and the certificate within a header file. You'll never develop firmware that way and send it to customers. The reason is that every single device needs to have a unique identity in order to track it, okay? And that identity needs to be immutable, and it needs to be protected, and ideally in an enclave that's tamper-proof. So what you're not going to do when you're developing your devices and sending them to a contract manufacturer is having a mechanism to create a private key and just lay it down to non-volatile flash, because a bad actor can just lift that directly off the flash. A script kiddie can do that, right? So if someone knows, if a bad actor knows that that device is vulnerable to that, and I'm going to go fix your HVAC unit and I see that device, I could lift the personal identity off that device. I can be crafty that way, right? That's script kiddie type of stuff. However, there is a logistical challenge in getting the certificate on these devices. In order to get the certificate on the devices, if you want the certificate on the device, when your customer receives the device, that means that you need to get the certificate on the device during the manufacturing process. If you don't want to do that, a way to overcome the provisioning challenge is to use a method to leverage the private key that's already on the device, usually within a secure enclave, or a secure element, or a TPM, and use that to create a CSR, which you can then issue up into the cloud. All right? Then the cloud can do some cross-checking, which I'll talk about in a little bit later, and then generate a certificate for you, and then send it back to the device, and then you can connect to IoT Core. So this is what I call lazy loading a certificate in a process that I developed with Texas Instruments earlier this year. What's also very common is what I've been working with Microchip on for the last several years is by using a integrated circuit called the ECC 508A and the 608A. This is a little breakout board that I have, which is, has a SAMD21 processor on it and a few different flavors of secure elements. One is from a solution that's called Trust and Go. With Trust and Go, you don't need to bring your own certificate. You don't need to do just-in-time provisioning or any of that. We have a new service that's in beta right now, which enables you to import certificates to AWS IoT Core without having a certificate authority registered in IoT Core. So that's how Trust and Go works, right? You can just import these certificates, and the way that works is you buy the part from Microchip, and they'll send the roll of parts to your contract manufacturer, and then within Microchip Direct, they'll give you a manifest that you can download and then import into IoT Core, all right? That's already there. Another chip is called Trust Flex, and that has pre-provisioned certificate as well, but that's with BYOC. So you can use your own certificate authority, you register your certificate authority in IoT Core, and then you can have your customers first connect to IoT Core and use just-in-time provisioning or just-in-time registration to register that certificate on the fly. The one I'm going to talk about later, though, is called Trust Custom, where you get a blank secure element. Still, you have an immutable private key, but you can use that lazy loading that I talked about in order to get a certificate provision to your device. But wait, there's more. There's even providers out there like Secure Things and Data.io. They're partners of ours. Actually, Secure Things is now owned by IAR. And that's like a full white glove service for provisioning. So if you want to really, really simplify the process for provisioning, those partners will help you out as well. So let's take a look in detail what that lazy loading looks like. In order to do that lazy loading, I need to do whitelisting. Why? Because I need to authenticate the device before I provide it a certificate, okay? So the first step is getting some information off the device. So that means on the manufacturing line, you need to use a test dongle to extract something you have and something that you know. In order to just do security and provide credentials, those are the two things that you need to have. It's just like when you're entering your password and then you're doing your one-time password after that, all right? So in order to achieve that, you can extract the serial number off of the ECC 608A, and you can do that off the TI part as well. And you also need to get something that, well, because something that you have is the secure element, something that you know is the private key, your unique identity. But if it's immutable and can't be read into main memory on the device, so what do I do? Well, what you can do is extract the mathematical representation or mathematical counterpart to the private key, which is the public key. So you extract the private key, you extract the public key and the serial number, create a manifest, and you can upload that up into DynamoDB. The second step you need to do is leverage a service up in the AWS cloud called AWS Certificate Manager Private CA. So you can bring your own certificate, right? In order to do that, though, you need to issue a CA from likely your own signer. right? So you have your own security team, they manage their own HSM. What you will have to do is go to ACM PCA, issue a CSR for that CA, bring it to your security team. They issue an X509 certificate that represents the CA, the intermediate that you want to load into ACM PCA. And the issuer is your CA, right? So now once you have that CA implemented within ACM PCA, wow, that's like a lot of acronyms, right? So once you have it in there, now you can generate client certificates from ACM PCA. So you import your client certificate after it gets issued by your HSM, but wait, there's more. You need to actually import that CA into IoT Core in order to get those certificates registered, right? So that's the management part. That part happens before your product hits the shelves, all right? So what happens when your customer goes and buys the device? Well, your customer's gonna bring it home and turn it on, and your firmware is gonna check, hey, I don't have a certificate. So now what I need to do is talk to API Gateway and get my certificate issued. What the device is doing is sending up a CSR. The CSR contains the public key. The CSR also contains a subject line. Part of that subject line is the CN value in the subject line. The method that we're using here to propagate the serial number up into the system is by putting the serial number as part of that subject line as the CN value. So now I have the something I have and the something I know, and I need to authorize. I'm not going to just willy-nilly issue a certificate, so I'm going to send that to a custom authorizer. I think now they call them Lambda authorizers, not supposed to say custom authorizer. And what that does is it says, okay, I have a serial number because I extracted it from the subject line from the CSR, and I'm going to go find the public key into the device that I whitelisted, and when it finds it, then I'm going to do a comparison. If it doesn't find it, then I'm going to return a 403 back to API Gateway. Then I'm going, if it does find it also, sorry, you have to compare the public keys, the public key that's in your CSR and the public key that you just got from DynamoDB. If it's good, return a 200. If it's bad, send back a 403 to API Gateway. If it's good, then now you can get the certificate provision. So you hit up Lambda again, you get the certificate provision from ACM PCA, send the certificate back to the Lambda function. But wait, now I can actually overcome that device bump when I do jitter or JIT-P. So from this perspective, I have the certificate. I know what my thing name is because it's usually the serial number, still because it relates to what you're generating or what the device identity is. So now I can import the certificate directly into IoT Core. I can generate the thing, and I can make the relationships between the thing and the certificate and the policy and the certificate, and I'm good to go. Now I can return back the certificate to API Gateway, give that back to the device, and now we can connect to IoT Core. Everything's good, right? That's lazy loading. So when I want to do that in detail is, even though I did this system initially with TI, what I'm representing in these next series of cases is doing it with the Trust Custom solution as well, just to demonstrate that this pattern is applicable across multiple microcontrollers. So you need to initialize your device identity, right? Your private key. It's immutable. You can't take it off. You can't read it into main memory. You can't. Actually, the ECC 508A and 608A is even tamper-proof. So side channel attacks don't work on that IC, all right? But I have to get together my device identity, whitelist my device, provision it, and connect to the cloud. So these API calls are actually coming from the Microchip CryptoAuth SDK. I didn't make up these API calls. So I want to initialize the device. I'm going to turn on the IC on the manufacturing line. I'm then going to initialize the private key. I get no secret back on the manufacturing line. No secrets at all. The next step on the manufacturing line in the test dongle, I need to extract the serial number off the IC. That's just an easy API call. The next step is I need to get the public key from the device. I can't extract the private key into main memory. I can't extract the private key from the IC. So I'm going to make a crypto call into the device, right, in order to get the public key derived from the private key because they have that mathematical relationship. So I create a structure, the microcontroller talks to the IC over I2C, gets the bits back, which represents the public key when I do that API call, and then it fills out the structure, and then I can get the public key from that structure. From there, you can emit the serial number in the public key over serial. This is public information. There's nothing private about a certificate. It's public information. The serial number, there's nothing you can do with the serial number unless you have the public key, which has the mathematical representation to the private key. So you're still good. Then you can send that up into DynamoDB. This is okay for prototyping. Please don't use this command when you're importing tens of thousands of individual devices up into your manifest whitelisting, because you'll probably get throttled in about 3 seconds, all right? So you'll want to batch process that when you're doing that at scale. The next step is what happens when my customer turns on the device. You need to implement firmware to do this. Remember, your private key has already been initialized. Your device has been whitelisted up in the AWS cloud. The first thing I need to do is I need to create the CSR, because that's what I'm going to send as API gateway. The secure element has X509 APIs there, so it can actually, you can construct a CSR using the CryptoAuth SDK, and it interoperates with the secure element. Some modules, though, now what I need to do is I need to interact from the microcontroller perspective up into the AWS cloud. Some microcontrollers offload HTTP client to their communications module. The CC3220SF actually does that. But the one that we typically use, which is the Wink 1510 with microchip, does not offload. So in this particular case, I need to implement an HTTP client on the microcontroller, which takes additional, just warning, open disclosure, takes additional flash, takes additional memory in order to run that on your microcontroller. But then you can make that post to the cloud and then get a response back, and now you have your certificate. The secure element has a thing called slots, which can not only store private keys, but can also store certificates, just for safekeeping. But when you have a Wi-Fi controller, usually what you're doing is that you're offloading your TCP and TLS stack to that microcontroller. In order to facilitate that communication, you're putting the certificate on the Wi-Fi module as well. But you're probably thinking, well, if that's doing the secure connection, then how am I going to do my TLS 1.2 connection, because my Wi-Fi module doesn't have the private key, right? The private key is in the secure element. So what Microchip did is actually set up some special routines in order to have access to the secure element in order to do the Diffie-Hellman exchange during the TLS 1.2 handshake. If you don't have access to the private key, you can't generate your ephemeral keys, and then you're toast. It doesn't work, right? But they implemented that. So now you have your certificate and you can make your connection. In Amazon FreeRTOS earlier this year, we changed the networking layer and the MQTT client in Amazon FreeRTOS. That was the 2019-06 release. We're now using the embedded C SDK within Amazon FreeRTOS, so we get some synergies there. You just need to make up a couple of structures. I won't say that these structures are trivial to implement, but they're a lot more helpful than doing, like, working with PAHO directly. And then you're able to make that connection in the cloud, and when everything handshakes good, like, for example, your certificate is still activated in IoT Core, then you can make that connection to the cloud. So to recap, all right, on what we just talked about, because we just went through a whole bunch of stuff. First is connectivity patterns reduce the basic threats that you have. Those are the communication patterns that I just talked about. And we have been talking to customers about securely connecting to IoT Core ever since we started shipping IoT Core to our customers, all right? You just need to have some additional insight into tying down the security on your devices so your bad actors can't get a hold of the private keys and start impersonating your customers and then stealing personal identifiable information. So that means that you really, really want to protect the device identity. But there are more things that you need to take care of that I talked about in the second section, which is we need to be able to maintain the security profile of your devices over time. So we need to take care of how we do OTA updates. That's not something that you think about after you ship your device. That's something that you think about before you ship your device. Skipped ahead. And so, what you implement today is not what you need to take care of tomorrow. Yes, people should be staying awake at night. If you're doing with security every day, you should be actively mitigating this every single day. They're ever evolving. So, all of these prototypes will be released to GitHub after reInvent, sometime hopefully before Christmas, hopefully. And this demo happened on Wednesday, so you can't go to it, right? Unless you have a time machine. So with that, thank you. That's my contact information. You can follow me on LinkedIn or wherever. I'll post when things come live. I have other GitHub repositories you might be interested in. Please go take a look, and thank you very much. And if you have any questions, you can come up after. I'm a little bit over time. But please do the session feedback. I do read the feedback. Okay, thank you very much.